In this section, we're going to talk about how to find equations of lines and planes in 3 dimensions. And this is a really good section. You're really going to want to spend some time on this section because even though the concepts are very basic, some of the problems can be challenging because they require us to think in 3 dimensions. So this will be good for our visualizing 3-dimension skills, which we're really going to need in this course. You can ignore this. This is from a previous class where I covered it in class. This video is going to cover this material. So I break this section into 2 pieces. The first one is where we're talking about the lines, and the second one is where we're talking about the planes. The first part I called 12.5 part 1, just to break it apart. All right, so how are we going to get equations of lines in 3 dimensions? So first of all, let's look back at 2 dimensions. If I have a curve in 2 dimensions, I can express it as a single equation in 2 variables. So for instance, something like this, that's a curve in 2 dimensions. It's a parabola. For a line in 2 dimensions, we would have to have the variables to the first power like that. But any equation in 2 variables will be some sort of 2-dimensional curve. And we already mentioned that anytime we have an equation in 3 variables, it's not a curve, it's a surface. So if we're trying to get at how are we going to express a curve or a line in 3 dimensions, it doesn't sound like we're going to be able to just use an equation, because an equation in 3 variables is a surface, not a curve. Well, let's go back to 2 dimensions for just a minute. This was one of the ways that we could express a curve. We also could use function notation. So if we had f of x equals, for instance, 5x plus 9, that's a way to express a line. And any other function of one variable that we write down will also be a curve. The other way that we had for expressing the equation of a line is a pair of parametric equations. Like, for instance, x equals 3t, y equals 4t plus 1. It's going to be really important that you've reviewed section 10.1 here. If not now, then for sure before the beginning of the next chapter, you're going to want to review parametric equations. The parametric equations, we write 2 equations, and those 2 equations, we can eliminate the parameter, and it would be equivalent to a single equation, 2 variables. This is just another way to express a line. So we have 3 different ways that we talked about the equation of a line. But again, how are we going to do that in R3? If I try to do it in a single equation, that's a surface. And even if I tried to do it some sort of function notation, when we will get to this actually later, we would have to have f of x and y equals something. But that turns out to be a surface also, because this output is corresponding to a 3rd variable. So I can't express it as a single equation in 3 variables or as some sort of function. The only way to express a curve in R3 is parametrically. That's an important point to get. That's why it's so important that we understand parametric equations in this class even more than we needed to in the last classes, because we're going to be using them a lot. Because if we want to talk about any sort of curve in 3 dimensions, that's the only way to express it parametrically. All right, so given that, how are we going to find the equation of a line? What kind of information would we need? In 2 dimensions, if we are given a point on the line, so suppose I'm given some point on the line, and I'm given the slope of the line. So the slope is the steepness. So in this case, for instance, it would be 2 over 1, the steepness. The slope would be 2 here. And given the point, we know that we can find the equation of that line using the point-slope form. So point and steepness, point and slope was all that we need. Let's think about that in 3 dimensions. If I gave you a point somewhere here, let's just go with the origin because I can draw it easily, and I said the steepness is, say, 2. So, you go up 2 units into the right one, and there's a line. There's a line with steepness of 2, and it goes through 0, 0. But is that the only line? that will work. If you think about it, here's this same line that I drew over here in 2 dimensions. But if I'm at that origin and I want a steepness of 2, I want to climb up something that steep, it's also that steep going forward here. If I come straight forward, it's the same steepness. If I go straight backward, it's the same steepness. If I go over here to the left, it's the same steepness. It's a steepness, think of it as a steepness of 2 going uphill. In fact, any path that I take along this cone, the steepness would be 2. So that information, point and slope, will give me a unique line in 2 dimensions. It doesn't in 3 dimensions, because if we give slope or steepness, there's a lot of lines with that same steepness. So what we have to do instead in 3 dimensions, instead of just giving a slope, is we give a direction vector. So if we're given a point, let's say this is our point P0, which is x0, y0, z0. And we're told that we want a line that is parallel to this vector. So let's call this vector V, ABC. So that gives us some sort of steepness, but we're not only saying just the steepness, we're saying this direction too. So from this point, you have to go parallel to this vector, like so. We're talking about this line that contains that point and is parallel to this vector. We're given a point and a direction vector that uniquely determines the line. Now, how do we find the equation of it? We're looking for a way to generate every possible point, x, y, z, on here. So specific given point, subscripts, x0, y0, z0, that's a fixed point on the line. We want an equation that will generate all of these. Notice for every point P on this line, if I formed the vector from P0, oops, that's P sub 0, P naught, to P, it has to be parallel to that red vector. So any vector from P0 to P has to be parallel to V. And we learned that for vectors to be parallel, one has to be a constant multiple of the other. Now I can use any parameter I want here. A lot of times we'll use k, but in this case, they use t, so I'll use t. That really is all you need to know. Now I'm going to break it down a little bit. P0 to P, form the vector from P0 to P, so we subtract x minus x0, y minus y0, z minus z0. Equals t times v, and v we called ABC. So that's a vector equation. We can think of that as a vector equation version of that line, but if we want to express it parametrically, then we'll break out each of the pieces here. So x minus x0 equals a times t. Next component, y minus y0 equals b times t, and z minus z0 equals c times t. And if we solve that for x, y, and z, we get x0 plus at, y equals y0 plus bt, and z equals z0 plus c times t. These are the parametric equations for a line that contain the point, let me kind of highlight here, the point x0, y0, z0, and the direction vector ABC. So the direction vector ABC and the point x0, y0, z0. So we just, the way I kind of remember this is the point goes here, the direction vector goes here with the parameter, and that is the set of parametric equations for a line. We'll look at an example in just a second, but while I'm here, I want to show you what they do sometimes with, I usually write the equation of a line that way. You will also see it written in vector form, but you will also see it in the book sometimes in what we call symmetric form. And all symmetric form is a rearrangement of this. If we took this first equation here and solved for t, the first equation, if I solve for t, would be x minus x0 over a. And we could do that for each one of these. And so sometimes what you'll see done is we just, if these are all t, then these are all equal. And you'll see the line written this way. So that's symmetric form. It doesn't really buy you much, but it looks a little more compact maybe. Don't be fooled into thinking we've now expressed the line as a single equation. I already said that that wouldn't work. Those would be a surface. It's really 1, 2, 3 pairs of equations. So it's not technically a single equation. If you're given the equation of the line in this form, sometimes you're given a line and then you have to figure out what a point on the line is and what a direction vector. And you can pull that right off here, the coefficients of t here, and here it will be the values in the denominator. Likewise, you can find the point here. Okay, let's take a look at an example. So this first example is a very straightforward example. You're given actually the point and the direction vector directly. So not a whole lot of detective work needs to be done here. We just put the point in here, the direction vector in here. So I usually kind of do it in that order even just to keep myself organized here. The point is 2, 6, 1, and the direction vector is 1/2, -3, 4. All right, you see how I just put the point here and the direction vector there? And this is the set of parametric equations. But let me show you something here. If this is v, then 2v, for instance, would be 1, -6, 8. And 2 times v is parallel to v. So if we're saying we want a line in the direction of 1/2, -3, 4, something over here, I'm not drawing it accurately, that would be my direction vector v. Now 2 times v looks like this. Should look parallel there. So I should be able to use this same direction, this vector here, to generate the same line. They're parallel. So if we're talking about a line that's parallel to v, that same line would be parallel to 2 times v. So when you're told the direction vector, you can actually use any multiple of it. The reason I mention that is because you might look in the back of the book and they might have this for the answer. Maybe they use, this is the direction vector. So 0.261 and direction vector 1, -6, 8. And so when you go to check your answer in the back of the book, it doesn't look the same, and you think, I've got a different line. They're not. They're the same line. Parameterization, something that you should have learned back in section 10.1, is not unique. There are many different ways to parameterize any given curve. So if we're going to want to know, well, is my answer right? Sometimes it's easy to tell because here we see we have the same point and this is a multiple of this, so it's pretty easy to see. But if I had used a different point on the line than you did, if I knew a different point and I used a different point here, it's kind of hard to tell if these both represent the same line, and we'll talk about how we're going to do that as we go on. All right, but parameterization of any curve, not unique. All right, these problems in this section can get pretty interesting. Some of them can get pretty challenging, but they all boil down to you need a point and you need a direction vector. But you're not going to be given them directly. I can guarantee I'm not going to give you a problem on the test where I say, here's the point, here's the direction vector, plug it in the formula, because that's not very fun. That's not very challenging. So they get a little bit harder. Here's this one. This one is just a little bit harder. What if you were asked to find the equation of the line through 2 points? I like to usually remind myself what I need in order to do the problem. I need a point and I need a direction vector. I think this is a good technique to use too, because you want to show your work in such a way that somebody can really follow your thought process and not have to guess at what you were doing. Okay, so point. Well, they gave us 2. Take your pick. I'm going to pick 507 for no good reason. But you maybe pick this point. That's fine. If you do, our answers aren't going to look the same. And that's okay, because parameterization is not unique. And the direction vector. Well, they didn't give us a direction vector this time. But I have this point 3, 4, 1, and this point 3, 4, negative 1, and 507. And I don't have those drawn in, their proper location in space. And I want the line through that. And they didn't give me a direction vector. Well, I can make one. I can make the vector from here to here. I can make the vector from here to here. Anything along here. I could make a vector that, goes right here. Any vector in the direction here will work. So I'm going to choose to use these 2 points. So I'm going to choose this one. So I'm going to choose the vector -2, 4, -8. Now you just watched me explain that and point things out, so you know exactly where I got that from. But if you just right now looked here, you'd probably be going, what? Where did she get that from? So in terms of showing our work at this level, I expect a little more, professional presentation. Then I'm going to label these. I'll label this P and I'll label this Q. And so I'll say that I'm going to use for my direction vector, what did I use from Q to P? We could have used from P to Q, but we used QP. So label your work so somebody can follow your thought process. Once you have that, you should be able to find the equations of the line just fine. Why don't you go ahead and pause, make sure you got that. Now I've mentioned in some of the tips that I really strongly encourage you when I suggest that you pause and try something, I really encourage you to pause and try it. You get so much more out of it than if you just let the video keep running and just write down what I write down. It's very easy to tune out when you're watching somebody else do the work than having to think and do it yourself. Okay, so go ahead and finish that up. So if you use the point 507 like I did, you'd have 5. I didn't bother writing the 0 and 7. And the direction vector -2, 4, -8 is here. Yours might look different. Okay, we'll get into even more challenging problems once we get a little more into looking at planes, and then we'll come back and look at lines some more. One of the things that we're going to need to do a lot of as we go on is parameterize a line segment. The way you're going to parameterize a line segment is you're going to put a restriction on T that just gives you a piece of the line, but you'll see that in the short video that follows. We're going to be doing a lot of that as we go on. We're also going to look at finding equations of lines in 3 dimensions coming up next. Okay, so you can go try the problems from the first part of 12.5 part 1, a couple just straightforward finding equations of lines.